Hey everyone. Okay, so now that we've talked about HR diagrams and how once you've measured the temperature and the luminosity of a star, you can figure out more things about it, like the radius, the size, right? And so, what answers are you getting for Tool 13? Let's look at this here. All right, between star A and star B, which one has the higher temperature? Well, star A peaks in the violet, star B peaks in the red. So the star that peaks at the shorter, bluer wavelength must be the hotter star. So star A must be hotter than star B. Which one has the greater energy output? Well, remember, energy output of a star is another way of saying luminosity, right? So the luminosity of star A is going to be the total area under the curve, right? This whole area, right? Whereas the luminosity for star B is just going to be that bit right there. So yeah, the luminosity of A must be a lot brighter than the luminosity of B. Which one's larger in size? Well, does star A have a higher luminosity because it's bigger or because it's hotter? Well, we know it's hotter. We certainly know it's hotter. It doesn't have to be larger, right? Maybe the fact that A is brighter is purely because it's hotter and not because it has a larger surface area. So given that we have no numbers here to do some math and calculate their radii, the safest thing is to assume is that A is hotter, that we know for sure, and that the brightness, the luminosity is coming from the higher temperature, not from a larger size. So probably it's a good, safe assumption that they could conceivably be the same size. A and C, right? A and C, which one has the higher temperature? Well, A peaks in the violet, C peaks in the violet. If they both peak at the same wavelength, if they both peak at the same color, then they must be the same temperature because only the temperature determines the peak wavelength. So they must be the same. Which one has the greater energy output? Well, star A has the larger area under the curve than star C does, so A has the higher luminosity. All right. So remember, like I was saying a second ago, right? Remember that luminosity, right? The luminosity of a star is what? It's 4 pi times the radius squared sigma times temperature to the fourth power. So the 4, the pi, and the sigma are all constants. The only variables are the radius and the temperature. And so the star's luminosity depends on its size and its temperature. The star can be high luminosity either because it's big or because it's hot or both. So for star C here, for A and C rather, right? Does star A have a higher luminosity because it's hotter or because it's bigger? Well, it can only be because it's bigger, because star A is not hotter. We know that star A and star C are the same temperature. And if A and C are the same temperature, the only way that A can be brighter is if it's larger. All right, A and D. I lost my graph here. Okay. Pardon me. A and D. Which one's the higher temperature? Well, A peaks in the violet. D peaks in the red. So the hotter star must be the bluer one. A it is. Which one has the greater energy output? Well, we were looking at these two stars in the last micro task, weren't we? The greater energy output depends on the area under the curve. So which star has the greater area under the curve? A has A's curve is this big one here, but D looks even bigger, right? D looks like it has an even larger area under the curve, so it has a larger luminosity. So how can that be, right? How can star D be brighter than A even though A is hotter? Well, D must be that much larger to make up for it. Right? The only way that star D can be brighter than A while A is hotter is if it's that much larger to make up for it, right? Star A's luminosity, right? Star A's luminosity comes from the fact that it's hotter, but D is cooler. Star D is cooler, so star D must have a really big radius to make up for its low temperature to create an even brighter luminosity. Okay? All right. So now we've got these 4 stars, A, B, C, D, and we've plotted them on an HR diagram. Indicate where the following are on the graph. Where are the large stars? Well, the large stars are in the upper right corner rather. The small stars are in the lower left corner, right? That's why these stars up here are called red supergiants, because they're red and they're supergiant. The stars down here are called white dwarfs because they're white hot, right? They're really hot, but they're dim. Why are they so dim even though they're hot? They must be really small. Hence, white dwarfs. Circle the 2 stars that could... So the smallest star here must be C, the largest star must be D, and the 2 stars that could be the same size are A and B, just like we said from the Planck functions on the previous page, right? If radius increases going from lower left to upper right, then smaller, medium size, larger, right? A and B could conceivably be the same size, just like we said here, right? A and B could be the same size, and the only reason why A is brighter is because it's hotter. The only reason why B is dimmer is because it's cooler, even though they have the same radius. Okay. So just by eyeballing where a star sits on an HR diagram, you can get a pretty good idea about how big it is, right? Small, medium, large. But if you want to actually calculate what the radius is, if you want to actually know what the radius is, then you can calculate the radius in solar radii. So this equation has been written in solar units. In other words, you'll calculate the radius of that star in solar radii, so compared to the sun, by plugging in the luminosity in solar luminosities and the temperature in Kelvin. Right? And the other thing that you know about HR diagrams is that these stars here, this is the main sequence right here, right? There's the main sequence right there. And what you know is that if you're looking at main sequence stars, then the luminosity of that star and the temperature are determined by the mass. So this top equation for the radius, that'll get you the radius for any star. This bottom equation here will give you the mass of the star if you know its luminosity, but this is only for main sequence stars, right? The relationship, this relationship between mass and luminosity only holds for main sequence stars. All right, so let's see if you practice problems here. All right, use the luminosity and wavelength graph to determine the correct ranking for the sizes of stars H, J, and K, from largest to smallest. So this looks a little complicated, right? When you're stacking all of these Planck functions on top of each other, this can look a little complicated, right? Figuring out which star is the big one, which star is the small one, which one is in the middle, that was a lot easier here. So let's just do the same thing, right? Let's look at an HR diagram, right? Remember how all HR diagrams are laid out the same way, right? Luminosity is on this axis, temperature's on this axis, and the bright stars are on top. The dim stars are on the bottom. The hot stars are on the left side, and the cooler stars are on the right side. So let's look at these 3 stars, H, J, and K, and see where they would plot these 3 stars on an HR diagram. So let's look at H first here. All right. Is H, is it hot or is it cool? Well, it's peaking in the red, so that's going to be a pretty cool star. So it's going to be over here. Is H bright or is it dim? Well, it looks like it's got a big area under the curve, so that's going to make it bright. So star H is cool and bright, so that's where that star would sit on the HR diagram. How about J? Is J hot or cool? Well, J is peaking in the violet, so that makes it pretty hot. Does it have a large area under the curve or a small one? Pretty big, right? So star J has a large area under the curve. It must be bright. So star J is hot and bright. So that puts it right about there. How about K, right? Is K hot or is it cool? K is also peaking in the violet, so that's going to be hot. But it has a low area under the curve, right? It doesn't have much of an area under the curve, so that's going to be a dimmer star. So K is hot, but it's dim. So now this is going to make it, looking at the HR diagram is considerably simpler than looking at this big mess. Which star, now remember, the radius increases, right? The radius increases going, that's supposed to be an up arrow. The radius increases going from lower left to upper right. So which one's the small one? K. So which one's the smallest? K. Which one's in the middle? J. And which one's the largest? H it is. There we go. Suppose star A gives off the same amount of energy as star B, but star A is hotter than B. So, what would that look like? Right? Luminosity, temperature. What would that look like on an HR diagram? A gives off the same amount of energy as star B. So they have the same luminosity, but star A is hotter than star B. So A would be here, and B would be right there. Right? Same luminosity, but A is hotter and B is cooler. What can you say about the sizes of A and B? Well, if B, the large stars are up here, the small stars are down here, if star B is closer to the upper right, star B must be larger. Right? Why? Because if these two stars are the same luminosity, remember, luminosity can come from temperature and or size. Is star A getting its luminosity from temperature or size? Well, we know it's hot, so it's probably getting its luminosity from it being hotter. How can star B be just as bright even though it's cooler? Well, then it must be larger to make up for it. So B must be the larger star. And the smaller stars are down here. So B must be larger than A, which is that one right there. Yep, that's all we need to know. All right. So we've got three example stars here. All right, we've got three stars, and we know they're main sequence stars. Right? So if they're main sequence stars, then we know where'd that page go? Right? If these stars are both if all three of these are main sequence stars, that means both of these equations hold, right? The radius equation always holds, and this mass relation holds if they're main sequence stars. So we got the luminosity, we got the temperature. Let's calculate the radius and the mass. Let me pull up my spreadsheet here. Okay, and here it is. I already have the radius and the mass here. I already have the formulas in, so I had this left over before. Let's clean this up and start fresh for you. Okay. All right. So we've got, here's the spreadsheet that I had left over from before, and remember the way I had this set up, right? I've got my inputs in this column and my outputs in this column, right? The things that I'm entering are on the left side, and the calculations for your answers are on the right side. So I'm going to, have this equation here uses the parallax and the flux to calculate the luminosity. This cell here takes the peak wavelength to calculate the temperature. So now I'm going to take those and put them over here. Luminosity, temperature. Here, the luminosity here is in solar luminosities, just like before, and the temperature's in Kelvin, just like before, because look up our equations here. Make a little room here to work. Okay, here are our equations. Now the luminosity and the temperature are our inputs, right? Those are the variables that we're going to enter in order to calculate the radius and the mass. So let's look at our first example here, right? Okay. The first problem with the B-type star has a luminosity of 3160 and a temperature of 18,600 Kelvin. All right. So the formula for the radius is going to be, right, the radius equals, we'll open a parenthesis here, take the luminosity, right? It's the luminosity to the, no, stop that. Sorry, I mistyped here. All right, so grab the luminosity, take it to the 0.5 power, right? Take that to the 1/2 power, okay? And then divide by the temperature. What's the temperature? It's whatever number I put in B9. Temperature divided by 5800, and then square that, right? So I got the luminosity to the 1/2 power, check. I got temperature over 5800, and then square that on the bottom, check. And then I divide them. Good. Okay, this must be the right answer. So that star is 5.5 times the radius of the sun, right? Remember, this equation only works if the luminosity is in solar luminosities, the temperature's in Kelvin, and we get the radius of the star out in solar radii. Okay. The mass is going to equal, right? Start with equals, all right? The mass of this star, since we know it's a main sequence star, the mass is the luminosity, and then raise it to the 1/3.5 power. Okay? And that star is, I think it's fair to say, let's just round that to 10 solar masses. A word of caution, right? Let's go back here. You want to make sure that you keep these parentheses, right? Because you want to do 1 divided by 3.5, and that whole value, 1/3.5, that is the exponent on luminosity, right? You got to make sure that you keep the parentheses, because if you just did this, if you did luminosity to the first power divided by 3.5, right? The spreadsheet knows the order of operations, right? If you just did this, the spreadsheet would take the luminosity, raise it to the first power, and then just divide that by 3.5, which would give you an answer of 900, whereas the right answer should be 10. Right? So, got to be careful and include those parentheses. That way it takes the luminosity and raises it to the correct power. Okay. Did we do our math right? Right? Okay, great. We programmed our spreadsheet to do some math. Or is it doing the math correctly? How can we check? Let's look at an HR diagram, right? If, here we got it, right? Here's our HR diagram. if this star has a luminosity of 3,000 solar luminosities, right? Well, here's the luminosity on the vertical axis, right? 10, 100, 1,000, 10,000. Okay, well, if that star has a radius of 3,000 solar luminosities, that's a luminosity right about here. And it has a temperature of 18,000 Kelvin. Well, here's 10,000, here's 30,000. So let's say 10,000. Let's assume that's like 20. Well, look at the tick marks here, right? 10,000, 20,000, 30,000. Okay, so it's got a temperature right about here. So this star has a temperature of 18,000, a luminosity of 3,000. So that star should be right about here on the HR diagram, which means that what's the mass? Well, hey, there it is. 10 solar masses right there. So we must have our mass about right. Just like we expected. Our math says that the radius should be 5.5 solar radii. So what's look, these lines here, these gray lines here are lines for the radii of the stars, right? Any star sitting on this line will have a radius of 1 solar radius. Any star sitting on this line will have a radius of 10 solar radii. And our star right about here is right in between there. So here's 1, here's 10, 5.5 right there seems pretty reasonable. You can always sanity check your answers by just eyeballing the HR diagram. This is why HR diagrams are such a useful tool, is that you can always just eyeball this, look at the graph and estimate. 18,000 Kelvin, 3,000 solar radii. Okay, that star is, something very similar to Bellatrix. And that means that the mass should be about 10 and the radius should be, less than 10 solar radii. So, 3, 5, something like that. And then if you do your work and it comes out with 5 solar radii and 10 solar masses, then bingo, you must have the right answer. Always a good way to check your work. Okay, so how about the next one? How about the G-type star? 1 solar luminosity, 5,800 Kelvin. Well, can you think of a star that has a luminosity of 1 solar luminosity and a temperature of 5,800 Kelvin? Well, that's the sun. So this star must be something really similar to the sun. And so we would expect that it has a radius like the sun and a mass like the sun. Makes sense. Let's check our HR diagram and see if that makes sense. All right. Let's see. If that's 6,000 Kelvin, then 5,800 Kelvin is going to be pretty close to that. And 1 solar luminosity. All right. So sure enough, that star is like the sun right there. And it has 1 solar mass. It's kind of hard to read right there, right in the purple. But yeah, 1 solar mass, and it's right along this gray line here, the line of stars that have 1 solar radius. So 1 solar radius, 1 solar mass, 1 solar luminosity, that's the sun. Okay, how about what's the luminosity, or the mass? No, sorry, luminosity. Luminosity is 0.015 solar luminosities and a temperature of 3,150 Kelvin. All right, that's a radius of 0.4 solar radii and a 0.3 solar mass star. Makes sense, right? This is a star that is dimmer than the sun. It's cooler than the sun. It's smaller than the sun. Why is it dimmer and cooler and smaller? Because it's lower mass than the sun, right? Remember, the mass of a main sequence star is the one property that determines everything else for main sequence stars. And so that's what you'd expect, is a 0.01, right? So 0.01 solar luminosities, it's probably maybe right about there, right? So 0.015 solar luminosities and 3,000 Kelvin, that's going to be right about there, sure enough, stars that have 0.3 solar masses, just like our math said. So if your math matches the way stars really behave and lie on the HR diagram, that's a good indication that you got the right answer. Well done. If we got that all done, now we know a whole bunch of things about stars. We can figure out luminosity, temperature, radius, mass. Awesome. Right? Now we're really off to the races figuring things out about stars. All right. If that makes sense, fantastic. Update your spreadsheet. Make sure that you can do that to make your life easier. And if that's all good with you, keep on moving. And if you're still a little stuck and confused, send in the questions. All right. Have a good one, everybody.